Hi, my name is Jacob Lee, ZID Z5418742. This is the Solar System experiment for Physics 1160. First off, Kepler's laws of planetary motion are a series of laws describing the motion of a planet around the Sun. The laws are as follows. First law, the orbit of a planet is an ellipse with the Sun at one foci. Second law, a line drawn from the planet to the Sun sweeps out equal areas during equal periods of time. Third law, a planet's orbital period squared is proportional to the semi-major axes of its orbit cubed. In question 1, the center of mass between the star and planet, otherwise known as a barycenter, is located very close to the center of the Sun. In question 4, the center of mass is still very close to the center of the Sun, but given the increase in the mass of the Earth, it would likely be slightly further from the center of the Sun, but not enough for a perceptible difference. Likewise, in question 7, where the mass of the Sun has been decreased to 0.5, the barycenter would again be further from the center of the Sun than question 1. We can see why this is from the equation for calculating the distance from the center of one body to the barycenter here. Taking r1 as the distance of the barycenter from the center of the Sun, in question 4, m2 is doubled, leading to a slight increase in r1. In question 7, m1 is halved, again leading to an increase in r1. Despite this, the barycenter is not so far from the center of the Sun that the Sun can be seen to be visibly moving. However, in the planet-Moon system, the masses of the Earth and Moon are much more similar compared to between the Sun and Earth, so m1 on m2 is much smaller, and in turn the distance of the Earth from the barycenter increases. Since this distance is greater, the Earth can be observed to orbit a barycenter located within itself, yet some distance from its center, creating a wobble effect. For the 2-scale model, the distance between each marking on the grid is 0.5 AU, as there are 2 intervals between the Sun and Earth by default, which are known to be 1 AU apart. Below are the results from question 14. As you can see, if we convert orbital period to Earth years and orbital distance to AU, the results come very close to fitting Kepler's third law of t squared equals a cubed, where t is orbital period and a is the length of the semi-major axes. Differences between predicted and experimental results can be attributed to limitations in measurement precision and human error when placing planets at specified distances. However, these results do overall match Kepler's third law. Question 15 asks which planet we'd expect to have the fastest orbital velocity. The answer to this is Mercury, chiefly because it is the closest planet to the Sun. Newton's inverse square law suggests that the force of gravity between two objects is inversely proportional to the square of the distance between them. Hence, since it is the closest planet to the Sun, it experiences more gravitational force from the Sun compared to a planet further away, increasing its orbital velocity. Conversely, we'd also expect Neptune, the furthest planet from the Sun, to be the planet with the slowest orbital velocity. Overall, I learned several things from this experiment. First, this experiment demonstrated the concepts of barycenters and how they relate to the mass of the bodies involved. It highlighted how there are many influences on the Sun, despite many being imperceptible, such as how the Sun is likely orbiting around a barycenter so close to its center that the movement can't be seen. It also highlighted to me how Kepler's first law may not always be true. For a planet of sufficient size, the barycenter may be located outside of the Sun, such that the Sun is not located at one foci of the planet's orbit anymore. Instead, the barycenter will be. Finally, I learned that an increase in orbital velocity can actually result in an increased orbital period. You would think that making a planet faster would make it complete its orbit quicker, but it can both slow the planet down and make its orbit shape much longer by conferring kinetic energy to it and allowing it to escape the gravitational pull of the Sun.